welcome everybody to another wonderful day of hash tables. Last time we were going to talk more about hash tables, and we ended up kind of doing a code review, which was all well and good. So, and we talked a little bit about makefiles and useful stuff like that. But today we're really going to get into more hash table stuff. So, oh yeah, and then we talked about auto pointers, the old term for it, but unique pointers, shared pointers, part of the memory include. All right, so let's talk about hash tables a little more. Let's clear this out. Okay. And let's say that we wanted to have a bunch of I don't know, people or something. And they'll have a name and a address and like a social security number. We could add more in, but this will kind of make the point. And we want to be able to quickly write them into a database and read from a database. And we want to do this using a hash table. Okay. So, all right. The most basic hash table would be like the one with chaining we did before. I'll show you kind of how to do it with linear probing today. That's one of the two ways that you have to implement for your hash table assignment. Due next Friday, I think. Maybe next Wednesday. Difficulty level like in South Park, fractured butthole. Okay. So yeah, we'll just make our own. Okay. So class hash table. And what we want to do is have a public interface that has void insert, takes in a t by const reference. And we want to have a delete, maybe. Can't call it delete, call it remove. And search or something. Actually, why don't we do a hash map? We'll do this. Okay, and so this will map between one thing and another thing. Okay, so you can have multiple type parameters and a template, and the first is usually t. The second is usually called u, just because I can't give you any better answer than that. Okay, so and void, this one's gonna be search. And actually we'll have search return a u, and we'll take in a t as the key. And I'll see why we're doing that in a second. Okay, T stands for type, and then U is just the letter after T. There you go. Okay. You believe it's due on Wednesday? It says it is. Yeah, we'll see how it goes. All right. So, if we're going to do an insert, then we're going to need to do a key, const type parameter key, and const U parameter value. Remove can just be based on the key, and search it'll return a U. Okay. So what we're going to do here is we're going to use one of these things in a person as the key. Now here's the thing about keys. Here's the thing about keys. They need to be unique. Okay. You can't use like somebody's address as their key, because if you say, hey, give me the person located at address 1234 Main Street, and there's two people living there, you don't know which one it is, right? So the keys need to be unique. There needs to be a one-to-one and onto mapping between a key and a person. So of the three options we have here, which one should we use for the key? Which one is guaranteed to be unique for each person? SSN. Yeah, and that's why we use SSNs in databases all the time, even though it's illegal to do so, which it is, unless your system is a legacy system that uses the SSN as an ID number prior to 1978 or something like that. It is illegal to use an SSN as an identifier, and everyone does it anyway. So, yep. And my college did. My college actually had our social security numbers printed right there on our ID cards. So when you'd go up to pay, using your points, like you'd be in the dorms, you'd have like 800 points for your food and whatever, you would give them your social security number, which just seems like a horrible like idea from a ID theft perspective, right? All right, we'll bill it to your account. What's your social? And you just announce it in front of like 50 people, Don't employees have some sort of ID number for that very reason? Yeah, like for example, everybody has a unique social student ID in the system so that you can be uniquely identified in the system. So not the best idea, I know. And they kept it for years, and I was like mad about it. And they finally changed it, like in the late '90s. At some point they're like, "Yeah, okay, this is a dumb idea." But yeah, for a good 20 years, they were just using your social as your student ID number. So I'm employee number 0012. Yep, exactly. Okay, so we will use SSN as key and person as value. All right, so what we're going to do is down here in main, we're going to make a hash map, linking a unsigned integer 64t with a person. So those are two things. We'll call this hash table. Okay, or HT for short. So we've got a hash map. So it's going to be mapping between a social and a person. So when we search for a person, we pass in the social. It's going to return a copy of the person back out. And we probably should add like a change or a modifier or something in there, but whatever. It's good enough. And so it's going to take a social as the key, and then it's going to return a person back out. Okay? And we can delete based on the key, and we insert based on the key and the value. Does this setup make sense before I get into any of the code? Like, you understand the T and the U, and like all you have to do is pass in the social, and then it'll delete the person. You don't have to pass in the whole person. All right. Okay. All right. So you can make another parameter here. We can have like an int size or whatever, if you want that, and then we can make a vector of use named table or whatever. And then in our constructor, we can have a hash map. Kind of interested in what's going on here. The indentation's not working. Did I forget something? No. Okay. Great. Okay. So we're going to have hash map constructor, and it's just going to resize the table. Table.resize. We're going to make it size. So we're just kind of a fixed size hash table. The standard library, like I said, it'll rescale itself. It'll resize itself. When it says in class, to the template, you can use an unsigned integer. Yes, you can. Yeah. You can use either class or type name. It doesn't matter. It makes no difference to C++. Like you can't pass in a submarine to type T. You could. I don't see why not. Yeah. Mapping, we can map between a person and a person if we wanted. Fine. But what you want for the key is for it to be a unique, kind of identifier. Type T is so we can use anything with it, yeah. So we'll have any one of these things can be used as a key. In this case, I'm using an unsigned 64-bit number. If you don't like typing that whole thing out, you can say using u64 equals unsigned integer 64t. Now, a social security number will fit it within an int, I think, but it's kind of close, and it gets kind of close to the maximum integer size, and so I don't like being close to boundaries like that. So if you want, we could use a U64 here, because I aliased it like that. If you don't like typing all that, it's up to you. It's up to you, 64. Okay, anyway. So, so this is going to make table size 1000. Okay, and we need to pass in a size here. So we're making the hash map of size 1000. And so we pass that in as the template parameter here, and then it resizes the vector here. And so this vector just creates 1,000 empty persons, basically. Now, the kicker is that we need to determine if each spot in the table is full or not. And so there's a couple different ways we can do this. We can say if the social security number is 0, because there is no 0 social security number in America, we can just use that to indicate that it's open. If you want. Do you want to do it that way? And like if it's been deleted, we can set its social security number to like 1 or something. I don't know who social security number 1 is, like Richard Nixon or something like that, I think. No, it's not Richard Nixon. We could. Who is social security number 1? Who is social security number 1? He was 055090001. Yeah. Would isEmpty work? IsEmpty would not work because this this vector here is got 1,000 people in it, and each of these are going to be basically initialized. We can have each one of those socials be 0, and so we could use a magic number if we wanted. You want to see it like a default filled hash map, but I'm gonna do it kind of more properly, and this is actually how it's done in your homework assignment. So I'll pop over there real fast. I'm just going to copy the code out. So basically, for every bucket using linear probing, you have to keep track of if the bucket is open. In other words, it's free for new data to come in, if it's been filled with data, or if it's been deleted. And the reason why we handle deleted like specially is because if you remember how linear probing works, if a spot's full, we go on to the next one. And that can cause problems if we just make it open, right? If we had a really small hash table here, and this is size 4, so if we insert the number 5, which bucket is this going to go into? If we're inserting the key 5, which bucket will this go into? You remember the formula? 1. So we're going to put the number 5 in here, but we need to like keep track of this, that this has been filled. So we're going to mark this as filled. Now, let's say we're going to insert the number 10. Where does the number 10 go? Which bucket does number 10 go into? 2. And so that one has to be marked as filled, and these are going to be marked as open in the meantime. Okay. Now let's insert the number 13. Which bucket does 13 go into? What happens if the table is full and you're using linear probing? Does it go back around to the front? It does, yeah. And so here's what happens. So 13 tries to come in here, but that spot's filled. So you go to the next one, and that spot's filled. You go to this one, oh, that one's open, and it goes in here. And so this one is now marked as filled. Now let's say we want to insert the number 22. Which bucket does 22 go into? Why would anyone ever want to use linear probing? Because the performance is actually better than chaining when the thing is mostly empty. So that's the reason to use linear probing. It's actually faster at very low levels. So, because every time you do chaining, there's an immediate pointer dereference. So you go to the spot, and then you have to immediately jump to another location in memory. And that's slower than just checking this. Okay, so yeah, so we're trying to insert 22 into here. 22 is full. So we check this spot. That one's full. We go off the edge of the map, right? And then we come in this way. So every time you go to the right, you have to modulus by 4. And so rather than checking bucket 4 and having a out of bounds error, we go into spot 0, and there we go. So this spot is now filled. And if we now try inserting the number 5, it will go into, or actually 5 is already in there. If we try inserting another number, it'll just go into infinite loop unless we have a check for that. So what you might want to do is track how many elements are in the hash table. And if it's full, just throw an exception saying, sorry, no can do. Sorry, baby Jesus, there is no room at the end. Just throw an exception. Okay. So the okay. I think it's cool how you can't go out of bounds by checking bucket module size. Yeah, and so what you do is you just go to the next bucket, right? And so the next bucket is going to be, key plus, you do key plus plus, and then you do, modulus the n, kind of thing, and you just keep wrapping around, That's a power of modulus. Okay. So this thing's all full. All right. Now let's delete something. Let's delete 5. Now if we were to delete 5, and if we were to mark this spot here as open, now it's going to present a problem. And the problem it's going to present is that if we try searching for 13, we're going to come in here and be like, oh, that spot's open, not found. Return false. And that's wrong because 13's in here, right? So what you have to do with delete is you have to special case it. So what you have to do with delete is you can't mark it as open again, you have to mark it as deleted. All right, so if you come in here and it's been deleted, then you still go to the next one. You go to the next one until either you hit an open spot or you get to the end of the array. Okay. And so we would find 13 in that case. Now, if you insert again and the spot is deleted, then you fill it. So spots never go back to being open, ever. And so over time, the performance of a linear probing hash table will go down. And so you can refresh the hash table by copying everything out into a new hash table if you want. Because eventually all the open spots will get taken out and your performance will degrade. This will never go back to open. Okay. So if you were to insert though, like, 9, then 9 would come in here and this D would become an F. Empty after deleted. So that's one way of doing it. Another way you can do it is you could, every time you delete, what you could do, like we deleted this one, what you could do is actually search everybody to the right and see if any of those are us, and then you can like steal them and put them in here. Like that, and then mark that one as open. Right. But that makes your deletes a lot more expensive. So I'm doing something called lazy deletion. Okay. Lazy deletion. So you just mark the bucket as deleted and move on with your life. Okay. So over here in the code, we've got this thing here, which has 3 possibilities. It's got opened, filled, and deleted. This is something called an enum. An enum list is an enumeration. It lists all possibilities for a value. We could just use like an integer or something for this, but I'm going to show you guys the properly done method of doing this. And so this actually creates a new type called status. And variables of type status can only have values of status : open, status : filled, or status : deleted. Okay. No other values are possible. If you used an integer to hold this, you could do like open is 0, filled is 1, deleted is 2. But then what if somebody puts a 7 in there? It's a good question. What do you get? I don't know. So coming back into here, we are going to make a enum class called status. This holds the status of each bucket. And then we will need a vector of statuses as well. And we're going to resize this as well to size, and it will default to open. So, status, Mr. Data. Okay, so this is how we're going to track this status of each bucket. Okay, so let's do this. Let's do some things here. Let's make some people. So we're going to make a person named anyone who wants to be in the hash table. Type your name, address, and social into the chat right now. We'll put it up on the code for YouTubers to steal your personal identification. Person Bill is equal to Bill Carney. My address is 1111 A Street. And my social is 1, 2, 3, 4, 5, 6, 7, 8. Alright. So person Jack. His name is Jack Sims. His address is the dumpster behind 7-Eleven. You know the one. His socials 69699 And then we got Aaron, who goes by Bob. Address is 123. That's not a valid address, Aaron. I can't accept that. 1, 2, 3, 4, 5, 6 Main Street, and his social is 4, 5, 6, 7 9s. Okay. Now, just be aware, you guys are going to get identity theft. You know, with all your info up like this. Just forewarned is forearmed. All right, Montoya. Thing D has crashed. Good. Yeah, I need your address too, Montoya, so I can identity theft you. 1, 2, 3, 4 Main Street, and your social is whatever. Okay. I don't know if that's actually your social or not. I can put it up. And then we got Otal. Address 44 Minefield of Doom. And 987654321. Okay. Good enough. Now, would you want to know these? Nah. In fact, I probably would be reading these from a file, you know, and immediately tossing them into the hash map. So, yeah, whatever. We'll just do this manually. Whatever. I don't care. So hash table dot insert, and so we're going to pass in bill dot ssn. It is caps, I think. Yeah, bill dot ssn and bill. So you see how this works? It's using my social as the place in the hash table to store the data, and then it's going to write all my data in at that location. Does that kind of help make the key value difference like obvious? Like why we do this? The word new caused a physical repulse to me. You need one more number on Montoya's SSN. Yeah, so just do it by hand, whatever. Okay. Is it supposed to be one curly, one regular? Lord, did I screw it up? Did I screw up somewhere? Ah, jeez. Yeah. Thank you. Okay. Jeez. No, other way around. Sorry. There we go. There we go. All right. And absolutely nothing happens because our hash table is empty and doesn't do anything. Cool. So, all right. So we got a blank hash table. We're inserting stuff. And then, we need to actually write the code now. All right. And then let's just something like cout search for person. This is going to yell at us because we don't have a double left arrow operator on a person. So we'll just write one of those real fast. ostream reference operator. Do you guys all remember how to do this? Have to make it a friend. Okay. Const person by reference p. And you just have to choose how it gets formatted when it gets printed to the screen. I don't know. Name. And I need p.name. And sn. And that's it. Okay, so that'll teach C++ how to print a person to the screen. Okay. CP reference, got to catch up on those streams. Yeah, if you don't have it memorized, it's fine. The only reason why I have it memorized is because I've written so many of them over the years, right? It's not the most easy to memorize thing in the world. Okay. So if we do this, it will probably, I don't know what this will do because it's not returning anything. It might segfault actually. Might be fun. Let's try this out. Error no matching call to search. Hash table search. Warning, no return statement. Let's see what it does. Segfault. Yeah. The reason why it's segfaulting is because this function is not returning anything, and we're we're trying to get its data, and it's not returning anything. So that's this is actually a warning. It should be an error, in my opinion. We should not do this. Let's just put in a dummy thing for now. Return table square bracket 0. So we're getting a blank person now. Better than a segfault, maybe. I don't know. Okay. When do you make it a friend? So friends, there's two uses for friend. I'm using friend here because friend means it's not actually part of the class. If I didn't have it as a friend, this won't compile because this is not a operator of the person class. It's a friend of the person class. And so by marking it as a friend, you can actually put it inside of the class, which is kind of where it belongs. If I didn't do it that way, I could do it like this, and this is the same. It's equivalent code. Because struct is a pods, everything's public. I actually don't need friend. Friend grants you access to other people's private members, right? Everything in here is public, so I didn't need to use friend at all. But if you want it inside of the class, which to me is kind of like where it belongs, you need to mark it as a friend, because if it's not a friend, then you're saying it's a member function, and it's not a member function of person. It can't be, because it would have to be a member function of ostream, and you can't modify ostream. Okay. So it's just a way of putting it inside of the class when it can't otherwise go there. All right, so here we go. Let's do a hash table. All right, so okay. So we need a hash function, and this will and it will take in something of type T. And it will return the bucket that it will go into. Okay. So This is a pretty easy hash function. If I spelled it key instead of t, it would work. So this is your easiest hash function. Now, if you're doing something operator ogre loading, I like that word, ogre loading. How is it not a member function? Okay, so if you have a member function like this, like if I have an operator plus or something, then the person is passed in as the left. I would be passed in as the left parameter. This can't be a member function of person because the left parameter is not the person. Person's the right parameter. Whenever you have a member function operator, you are always the left parameter. Right? You remember that from how we did, like, you know, int operator plus person, right hand side, return my social security number plus right hand side social security number. I'm always the left. And so this would be called, if you had two persons, if you had person A and B, you said A plus B. It calls operator plus on A, and A is passed in as the left-hand side. For this thing here, you're passed in as the right-hand side, and the language doesn't support that. So it is not a member function of person. It is, in fact, a global function. That's what the friend means. It's a global function. That just I happen to put inside the person class because it organizes better that way. If you did the global version of this here, then you have to pass in the left-hand side explicitly. Okay. If you do a member function, you don't have to pass in the left-hand side. If it's global, you have to pass the left and the right-hand side separately. So this is actually a global function that just by dint of having the friend keyword here can be put inside the class. So it's maybe less confusing to have it like this. I don't know. It's up to you. It's the same thing. Thank you for clarifying this makes sense. Is that int a different shade or is it just me? I don't know. So this is a basic hash function. Now, if you're doing something weird, like with strings, how do you hash a string to a bucket? What do you do? Like, which bucket should hello hash to? Total ASCII value? Maybe. Now, you start getting into like some interesting questions of like, a good hash function has to always give the same result with the same input, right? If it doesn't, then it'll be ambiguous which bucket you get. It's not useful. It should also scatter the values over the hash table well. And so if you were to add up all the ASCII values, then would it go to the same spot? I don't know. It's a good question. Maybe. First, you should mod the social. That's what we're doing. Yeah, we're just doing a social, so we don't have to worry about this. Just modulus, whatever. But like, for a string, yeah, LE and EL would go to the same place. Exactly. It's not going to scatter. And so that's kind of an interesting question, you know. Total ASCII modulus size. Yeah, but like EL and LE would go to the same place. And depending on your input, also the ASCII numbers are in a very narrow range, right, of values. I don't know. So the standard library, I can actually pull that up. CPP reference has a function called hash. And std hash will hash anything in the standard library, basically, all the basic types. And so it's got overloads for ints and bools and chars, and there should be one for string. There you go. So hash on string, and all the different Unicode variants thereof. Stand back, I've got Jimmy's. Interesting. Doesn't actually say how it's done. That's interesting. Okay. It's done somehow. Okay. So anyway, we don't have to worry about it. We're just using SSMs. So as long as whatever we're passing in for a key supports the modulus operator, it'll work fine. All right. So let's do this. Insert. So which bucket should we check first? So we're inserting. We're given a social of 1, 2, 3, 4, 5, 6, 7, 8. We're inserting into a hash table of size 1,000. Which bucket should we check first? We're doing a hash table. What do we do? One of the rows 6, 7, 8, modulus 1,000. All right. So which bucket is it? 6, 7, 8. Good. Okay. So let's get our initial bucket here. Say size key bucket is equal to hash function key, just like that. So this will give us number 678. Okay. And then let's see if it's open. So if that spot is open, if status dot at bucket equals status open. So if that spot's available, we're done, right? You guys with me on that? Do you understand what we're doing here? If that bucket that we hashed to is open, we just write the value in and we're done. Okay. So we're gonna write into the table dot at bucket is equal to value. So we just copy all the data of the person gets copied into the table, no worries. And we mark the status dot at bucket equal to status filled, and we return. That's it. Okay. Now what if it's not open? What do we do for linear probing? Give up? Cry? What do we do? Go to the next bucket. All right. So we say bucket plus plus, and bucket equals bucket modulus size. We could combine these into one line if you want. Cope, curl into a ball. Okay, and so this code will work just fine unless the hash table is full, in which case it will infinite loop. Okay. So this is going to go one bucket at a time, to the right, to the right, to the right, until it finds an open spot. When it finds the open spot, it writes it in, returns. If the hash table is full, yep. So what we could do is we could check for, there's a number of ways we could check for an infinite loop. We could have a counter that just runs every time. We could see if the bucket we came to was the same bucket that we started at. Another way would be to just keep track in the hash table of how many elements we have and just, update our, count. And once the hash table is full, throw an exception. What do you guys want to do? What if the bucket has a deleted status? Yes, thank you. Very good. You want to just keep track of how many times we've gone? All right. We'll call this one int runaway counter equals 0. Every time we go to the right, our runaway counter also increments by 1. And if runaway counter is greater than or equal to size, then we throw runtime error, or we can just return whatever. Just make life simple. Okay. Should we make an overflow method we can overload? I don't know. It's up to you. It should be an error of some sort, but I'm just having my code quit. So this notion of a runaway counter, by the way, is a fairly common practice. If you want to guarantee that your code won't run forever, and you have a while true loop, so every time the loop runs, just tick it up by 1, and if it exceeds some threshold, just kill the program. I've seen these used, in a lot of different contexts. Just like, we haven't found it by now. Probably not going to find it. Quit. That can give you a guarantee of runtime, right? Well, we're not going to check more than 1,000. And so, like, if your linear probing is, if you've had to probe more than 1,000 to the right, your linear probing table is probably not very performant. It's running 1,000 times slower than it should be. So I've seen things like that where like throw an exception and then maybe trigger a reallocation, right? Like if your thing runs for too long, then it's like, that's too slow. Let's make the thing twice as big, take everybody from the old one, insert them into the new one, get rid of the old one. So there's all sorts of different approaches you can do for that. See you, Jensen. Wouldn't it never go over size because we break at counter equals size? Do we break at counter equals size? Yeah. Oh, I see what you're saying. Yeah. So, what if runaway counter started at bigger than size? What if somebody passed in a size that's negative? It shouldn't happen. It should be an unsigned integer, honestly. But that's why I always use, like, even if it's impossible for the thing to get past it, I don't like using double equals. I typically use greater than or equals, just in case something horrible goes wrong. Like, what if, what if there was something like this, right? And it was going up by 2 accidentally. Then it would not hit exactly the double equals half the time, and then your thing would infinite loop, right? So it's just it's not any faster or slower. I just always tend to write my code in such a way that if something goes horribly wrong, if size is negative, which I probably shouldn't allow, if runaway counter accidentally goes up too quickly, if something, right? If runaway counter is ever greater than size, I want it to quit, right? It's a philosophical thing, and it's something that I've just developed over years of programming, where I've seen problems. Yeah, because like when you're writing the code originally, like it's not even a big deal. Like you can probably guarantee it, but like people will come in and modify things, and I just always like to have my code like just handle it. Like I don't like having my code like fail. And this is just one of the techniques that I've built up over the years, where if it did somehow go up too quickly, if there was an extra plus in there somewhere, it would catch it and kill the code. Murphy's Law proofing code. You can never Murphy's Law proof your code. You can only make your code Murphy's Law resistant. It's just safer. It is safer. Yeah. From a correctness point of view, it makes no difference. But just from a I've been programming for a long time perspective, and I've seen this very thing save my life on a number of occasions, I just always code this way. Okay, so that should be that. Is int and a template different? This thing here? No, it's just an int. It's just an integer. We're passing in the size. It's not a type, right? So here we're passing in a type. Here we're passing in a type. Here we're passing in an int. Okay. Why is int yellow? The int's yellow up here, right? And the int's yellow down here. Same yellow, I think. Isn't it? No? I don't know. I don't tell you. Okay. Can I make functions that return class types? A function that returns a type. Yeah, there's pretty. It's pretty common for containers to have something like this, right? Where like you can grab the value type of a vector, and that gives you the type that it's holding. Right. So yeah, if you want to grab like the type of thing that is being held by a vector, there's this thing here, : value type. Right. It looks the same to you. The while is slightly lighter. Oh yeah, interesting. Yeah, I don't know. Yeah. Problem solved. Okay, so there you go. Okay. Is this better? Dark blue? No, I can't do this to myself. I can't do this to myself. Here, do desert. My eyes, yes. Okay. So that is insert. What about for remove? What are we going to do for remove? What do we do for remove? Actually, let's not do remove first. Let's do search. Okay, so first thing we have to do is what? Can we use search for remove? Yeah, I don't see why not. Or, yeah, call search. If it's not in there, just return. Yeah, seems fine to me. Yeah. So what's the first thing we do? If we're doing a hash, we're doing a hash table, right? What do? We want to see if social security number 1234 is in the hash table somewhere. What do we do first? Do the bucket. Find which bucket it should be in. Hopefully it's there. First one. All right. In fact, I'm just gonna. I should just copy all this code. Paste that, so I don't have to retype everything. And here we go. So, so if we get to a spot and its status is filled, right? Because we're trying to see. Wait, hang on. Before we do that, if we get to a spot, actually, yeah. If we get to a spot and its bucket is open, what do we do? We return, right? But what do we return? I might have painted myself into a corner here because we have to return something, right? That funky monkey. Which person do we return? Maybe we should have made this a Boolean. I don't know. I don't tell you. Return false? No, we're returning a person. So what person do we return? Return person, name, data, not found. Not found, sweet. Social security number 0. Okay, so there's a problem, right? Yeah, how do you return something that doesn't exist? It's actually a really interesting question, right? And that's how like that's why the standard library, when you call find, it returns a pointer, right? So if it returns a pointer to the thing if it exists, and if the thing doesn't exist, it returns a pointer to end, right? So that you can indicate somehow that the thing doesn't exist. Our code, we're actually just returning a person. So, yeah, throwing an exception maybe, but you really don't want to throw an exception if somebody's not found. So, yeah, I'm just going to come up with a magic number here. It's not good. The Void Man, that's a great name. Okay. So it'll return Void Man if it's not found. Probably should have a better interface. I don't know what to tell you. Okay, so yeah, so we're gonna go through here, and if we ever get to an open bucket, then nope. And if we do find the thing, if status dot at bucket equals, well, we know it's gonna be filled now, right? So we're gonna have to check for that. So if table dot at bucket equals key, no, table dot at dot ssn equals key, no. We're kind of, yeah, this is not good. It's really not good. Because now we're not using a T anymore. We're using a person. You see that? We're actually going to need to write down the key, probably in addition to the. We're going to write down the keys as well. Alright, so when we insert, we're going to insert into the table, and we're going to insert the key value as well into a new vector I've made, and there you go. Because, I mean, this will compile as long as we're working with people, but it won't work with any other data type, right? So we can't do this. Okay, so if we found the right key, then we return table.at bucket. And there we go. Okay. Can we make person a template? Get rid of the or deleted in the if statement. Oh, yeah. Yep, absolutely. If it's deleted, you can't quit yet. That's absolutely right. If it's open, though, you know that it's not there. You return void man. Can't do this either. Can't do this. This is tying it to a person. So we're just going to have to return an empty T, like that. Or whatever. Whatever it is. Okay. And then this is correct otherwise. Okay. So if we ever get to an open spot, it's not found, we return an empty thing. Probably we should return an optional. You guys want to see the proper way of doing this? Let's see if this works first. So I've been writing a lot of code without testing it. Let's see if this works. No match for operator equals. Okay, keys.atBucket equals key. W equals key. Keys.atBucket equals key. Oh, that's. Needs to be a T there. Okay. Cannot convert from that to that, yeah. Well, not a T, right? We're returning a U. you. And there we go. So it works. All right. So do you want to see the proper way of doing this, though? Because right now, if we search for somebody who doesn't exist, it's going to return just a blank record. And, you know, I mean, I guess we could make the default constructor be void man or something. So if we search for Bill, it works. But if we search for I don't know, some random string, then it's going to return void man, right? And that's a magic number, right? And that's not a great way of doing a system, because what if somebody comes up with the name void man? You know, then your system's going to be like, you're not found, and they're like, but my name is void man, you know. So let me show you how to do the correct way of doing this. Now, some of you are like, well, we'll do a boolean, right? Like make this a bool, right? But now we can't return the person. So that sucks, right? So let me introduce you to the wonderful world of optionals. And so we are going to return an optional. So an optional will be returned, and we don't need this anymore. Okay. So an optional is kind of like the notion of like a pointer, right? A pointer can either point at something or point at nothing. And this is how you do that, how you handle that concept in value types without using a pointer, okay? So an optional either contains an optional angle bracket person, either contains a person or it contains nothing, okay? And it's similar to how a pointer is either a null pointer or it's pointing at something, right? So this means it points at nothing, null opt, not null pointer. And let's just do this like this. That works. Optional view. And now this is going to return so it's going to return an optional now. Okay. And so rather than returning an empty person, which is kind of an ugly hack, what we're going to do is return null opt to indicate nothing was there. Otherwise, we return a person. And so you notice how we can either return a person or we can return null opt, and it handles both. Okay. And then in your code, you can actually, I think, just say if op. I think we just do this. If op, cout op. I think that actually works. No, it doesn't like that. Key reference. There you go. See how it works like a pointer, right? So you basically say if it's not a null pointer, print it. Else cout no record found. Searching for my name twice. All right. There. You see that? So what we're doing now is we're returning an optional. And so an optional is like I said, it's like a pointer that can either point at something or point at nothing. And so you can check to see if it points at something by saying if it's not null. If it's not null, then you dereference it like that, and that prints out the record. If it is null, null opt, then it prints out no record found. And so this is the correct way of handling that sort of thing. So, there's a couple other shortcuts with it. I don't remember off the top of my head, but there's some other ways of like kind of compressing that down a little bit. Can't remember off the top of my head though. Wait, any questions about this? So you do a search. If it was found, then the thing's not null. You print out the thing. If it is not found, then this is null opt. Go. Yeah, it's all modern C++. When was optional introduced? '17. Yeah, pretty recent stuff. It's there for a reason. Without that, you have to do like an iterator or something like that. Or you return a null pointer or something like that. Yeah. Okay. Now the only thing left to do is remove. Now we've got 26 minutes left in class. So I think rather than me doing remove for you, because I think you should write it. It's your homework assignment, right? I think given what we have here, you should be able to figure it out. Maybe. You know, you got the status. You don't have to do a hash map like I did either. You can do a much simpler one. So you're just doing integers. Because I'm doing a hash map, we have to have one vector for the keys, one for the values, one for the status. You make it simpler if you want. But you should be able to write remove given what we have here, right? So if you hash to the spot, if it's open, it's not found, you return. If you find it, if it's been filled with the data, you set that spot to be deleted, and you're done. Okay. Do we need to include any of these fancy pointers in our hash maps? You shouldn't be writing a hash map. I mean, you can, I guess, but there's no need. Because for you, you're just storing integers. And so for an integer, you're not doing a map, you're doing a set. Okay. We're using a map because we're mapping between a social and a person. Right? Social security number is used to look up people in the hash table. Anytime you have a separate key and value, that's a map. For your assignment, you're just hashing integers. And so that's just a set. The key and the value are the same. So you don't need this, for example. In the homework, can we use a stud library list? Yes, you can. Double hash, quadratic probing time. Yeah. So let's talk about double hashing and quadratic. Okay. So for linear probing, this is the iconic linear probing. Right. The bucket's full. Go to the next one. Okay. This gets swapped out for quadratic. And double hashing. Okay. So this is basically the only line that changes for quadratic and double hashing. So for quadratic hashing, what you do is instead of going 1 to the right every time, pull up. One note. So we have size 10. And let's say we insert the number 16. Goes in here. Now, we insert the number 26. We go 1 to the right. Looks the same so far, right? So far, quadratic and linear are the same. Now, let's insert 36. So with quadratic, the step size changes each time. You try +1, then you try +4, you try +9, +16, +25, etc. So if we insert 36 or 46, or any other thing that hashes here, We check 1 to the right. That one's full. Then we check 4 to the right. Okay. 1, 2, 3, 4. Oh, that spot's open. Okay, let's put 46 in there. Okay. Let's try inserting 106. Okay. Try 1 to the right. That one's full. Try 4 to the right. That one's full. Try 9 to the right. 1, 2, 3. That one's available. You understand? So that's the only difference. That's quadratic hashing. Quadratic hashing and chaining are not the same. Chaining is when you do, that was the one I showed you last time, where every time you insert into a bucket, it goes into like a binary search tree or a linked list. That's chaining. Quadratic is when the step size isn't 1 every time, like it is for linear. The step size goes up quadratically, right? So you try 1 to the right, try 4 to the right, try 9 to the right, try 16 to the right, try 25 to the right. How do you avoid an infinite loop? The quadratic doesn't work if the load is over 50%. So if your quadratic hash table is more than 50% full, it will probably infinite loop. So put in a infinite loop checker, like we did. Right? Something like that. Okay. If you're chaining, should status... You don't need status at all if you're chaining. You don't need status at all. If you're doing chaining, you just have a bunch of linked lists or a bunch of binary search trees, and you just call insert on each one, and they will just handle themselves. Okay. And you can use the standard library linked list, or you can use the standard library BST. List or set are both perfectly valid. You just make an array of lists or an array of sets. Either way, they're probably going to be pretty similar in performance. Maybe not. I don't know. Try them out. See which one's faster. Okay. Yeah, you don't need status, though, in it, because these things keep track of their own status, like how many elements are in it and stuff like that. You can use the standard library list, yes. Okay, so let's talk about double hashing. This one takes a little bit more time. Do you understand quadratic? Like, it's basically just that. Instead of plus plus, you're going to have, maybe even, you could probably even use runaway counter here, right? So instead of plus plus, it's plus the square of the runaway counter, something like that. It's not that different. Yeah, it's literally just this line of code different. Okay. It's going to be the square, it's the square of the number of probes you've done from the original spot. So maybe you remember the original spot, and then you add 1. You remember the original spot, you add 4. Original spot plus 9. So it's just the bucket plus the runaway counter squared. I don't know. You guys are smart. You can figure it out. It's not anything hard. As long as you understand it conceptually. So as long as you guys get it. Quadratic will never check the same bucket twice before checking any spot for an n. Not necessarily. So the quadratic version will not guarantee you that it will find an open spot in a hash table. It can guarantee that up to half full. If the quadratic probe doesn't find something free, that doesn't mean that there are no free spots. Linear probing will find a free spot, right? It'll eventually go through every spot in the hash table and find an open spot and be like, that's the one. You know, we're 30,000 buckets in, but we found it. Here it is. Quadratic is not guaranteed to find an open spot. So there's that. Okay. I understand. In what case would you change C1 or C2? What is C1 or C2? I don't know. You're gonna have to give me a little more context on that. Okay, so let's do double. So double is a different beast. Formula gives for quadratic. Okay. Let's do double. So double is a different beast, and so double hashing requires a couple things. So first of all, double hashing requires your table is prime in size. Okay. So you have to have a hash table of prime size. And this is actually one of the downsides to double hashing. Is that, well, there's two downsides. First of all, sometimes, like if you're trying to benchmark things, you're like, I want to try 3 different things at size 1,000. Well, you can't, because 1,000 is not a prime number, right? So you have to make your double hashing version either the next prime up or the next time prime down, but either way, it's no longer an apples to apples comparison, right? And the other downside to it is that there's certain optimizations that, like the very fastest hash tables, oftentimes use powers of 2. And the reason why they do that is because you can modulus to a power of 2 very quickly. You guys know how to do that? Do you know how to do, like, if you wanted to modulus, like, I don't know, 128? This is like on most systems, this is somewhere around like 80 cycles or something like that. Do you know how to do this in 1 or 0 cycles? Anyone in my 45 class know? Yeah, you can do. You think you remember it? So you take the key, bitwise and what is that? Something like that, if I counted correctly. And this does a modulus of 128 in 0 or 1 cycles versus 80 cycles. Much, much faster. So if you're trying to squeeze absolute performance out of your hash table, a lot of times they use powers of 2, because the modulus is oftentimes, that's the performance killer, right? Because every time you go to the right, you're doing a modulus, right? That's actually what eats up most of your CPU cycles, is the modulus. And every time you hash something, it's a modulus. If you do double hashing, there's another modulus you're about to see. And so double hashing can't actually take advantage of this little one trick that doctors hate. Okay. So they don't use primes? What do you mean they don't use primes? You have to use primes if you're doing double hashing. But the fastest ones, yeah, they don't actually do double hashing. Okay. So there's that. There's that too. Okay. They don't use primes. Why did I learn so much mod p math? Well, yeah. Modulus is very useful. All right. So here we go. So for double hashing, what you do is you have a size of your hash table, and then you have another prime. And that prime is going to be smaller. I'll call it, I don't know, k or something. And you can pick any prime smaller than size. Okay. A lot of times they use the first prime smaller than size. It doesn't have to be. In fact, it's a tunable parameter due to caching effects. A lot of times they use a smaller value. It doesn't really matter. And the upshot is, let's say your size is 17, then your k could be like 13, right? It's a prime smaller than it. Could be 7, could be 11. Doesn't really matter. It'll matter for performance, but mathematically it doesn't matter. Okay. So the initial bucket is the key modulus size. Do not type and write at the same time. Key modulus size. And then the step size is equal to the key modulus k. That's the only difference. Okay, so when you're doing this here, bucket plus plus, if you're doing double hashing, it would be, instead of that, it would be like bucket plus equals step 2. And step 2 is key modulus. That's it. So one line of code changes, and you compute that like up here somewhere, right? So you get your initial bucket, and then you would compute like your your step, or whatever, would be like hash, you know, you do that, you know, that computation. So size key step 2 is equal to key modulus, okay, something like that. That's it. So that's really all it takes to do double hashing. So between linear probing, quadratic, double, there's a couple lines of code different, but basically they're very, very similar. And that's why I'm giving you the option of either doing them, you can either do double, you can either do quadratic, or you can use the standard library to see if your code's faster than the standard library's hash table. And I'm not really sure which one's actually going to be faster to code, because all of them are going to be pretty close in terms of like, I don't know, 3 or 4 lines of code. Like they're not bad. Okay. Are you guaranteed to find an open bucket with double hashing? Yes. And you'll understand the mathematical theory why when you take CSI 26. So if you have 2 prime numbers, and like let's say you have the number 13 and the number 7. If you keep adding 7 over and over again, and wrapping around every time, it'll eventually touch every bucket in the size 13 array. So that's why you learn mod P. Yes, your life was not wasted. So in CSI 26, you'll actually learn the theory of why you'll hit every bucket. For now, just trust your professor that if you do double hashing, you will eventually find every open bucket in the thing. Your K can be any prime smaller than size. That is correct. Yeah. Theory. Yeah, that's why. I mean, that's why computer science people study theory, right? I always learned that K had to be the biggest prime, smaller than size. That's how it was taught to me. But then, after I studied the theory, I'm like, oh wait, it doesn't have to be. The math works out the same once you've studied modular math and things like that. And in fact, a lot of times you might want to use a smaller K so that things are actually more tightly grouped, so that you get better cache performance. Yeah. So cache performance is something you learn about in CSI 45. Not too bad, I don't think. So that's kind of my spiel for today. What did we learn today? We learned quadratic hashing, double hashing. I gave you 2/3 of a hash table here. This is a hash map, of course. You don't have to do a hash map. You just have to do a hash table. Or a hash set, I guess. Learned about optional. Optional is kind of cool. Modern C++. If you took my class when I first started teaching, I wouldn't have been able to teach you that because it didn't exist yet. I would have probably told you to return a pointer or something, right? And return a null pointer if it's not found, and a pointer to it if it is found, something like that. But you don't need to do that anymore. Will this code be up in public? Sure. Move main.cc into public. There you go. If you can find it in public, you can access it. Security through obscurity. I'm kind of worried about messing up on one of these and making it so it isn't order 1. Would we stop being order 1 if we iterated through a list in a bucket? Now, see, it's order 1 on average, right? If you hit a bucket and you're in a list, yeah, it's going to be an order in search, right? But that's the nature of the beast, is that when you do chaining, you're in a list or you're in a binary search tree. It shouldn't be that long. If all of your things are hashing to the same bucket, your hash function has a problem. Remember what we talked about before? I can't even find this one. Public. Okay. Remember what we talked about before? Like your hash function needs to scatter the values. Like if everything is hitting the same bucket, you have a bad hash function, right? If everything hashes to bucket 13, then you have you're gonna have an order n for everything on your thing, right? So I wouldn't worry too much about it, Lopez. The main thing that I'm worried about is that people iterate over every bucket, right? And so if you're searching for the number 42, they'll go over bucket 1. Hey, is it in bucket 1's? No. Bucket 2? No. Bucket 3? No. No. That's wrong. With a hash table, you jump to the bucket You search there. When you're doing chaining, it's very straightforward. You jump to a bucket, and then you call find on the list or the binary search tree there. And that's it. If you jump there, you're good. What I didn't want to see from the student who went to UCSD was he would iterate over every bucket and call find on every bucket, which defeats the entire purpose of a hash table, right? The whole point is you can just jump to the right bucket and search that. Okay. Could you explain why the search part of the virtual class definition is const? Search is const because search should not change a hash table, right? If you are searching a hash table, that should not modify the hash table. I'd be very surprised if I called find on a hash table and it deleted something. You know what I mean? Like, it's when you search, hey, tell me true or false, is it in there? Yeah, it shouldn't be modifying, right? So it's marked as a const method. You put the const there, that means that it is not changing anything on the data structure. And you want to remember to set that. I forget a lot of the times because it just slips my mind. But whenever you make a method, a member function, you should always mark it as const if it does not change the object. Okay. So, make sure not to do that. That's the whole point. Yeah, that's good. It breaks your code. You took out the const and it was fine. You need, if that's the case, it's possible, I think, one of these were not marked as const. So rather than taking out const, put the const in here. So I think one of these was not marked const properly. So add the const down there instead of taking it out at the top. Why do the functions equal 0? This means that they are deleted. These are deleted functions. They do not exist. And so of the parent hash class, which is an abstract class or pure virtual class, it has no actual functions on it. Sims, have you ever seen, like, you did Java. Did you ever see an interface in Java? So an interface says in Java there's the sortable interface. And so the sortable interface it basically says if you are sortable, you implement the compares to function. And so this is the C++ version. This is the C++ version of an interface, where basically anybody who conforms to the hash interface that I've made here implements the following functions: insert, remove, search, and change. And all of the kids will do these 4 things. So it's providing an interface, and then the different implementations will implement these in different ways. Like chaining is different than linear probing, which is different from double, which is different from quadratic, which is different from using the standard library. Okay. But as long as each of the children follows this interface, then everything works out beautifully. Is inheritance a 41 topic? Yes, it is. In fact, that's coming up. So stay tuned. I don't like inheritance very much, but in some cases like this, it actually works out really well. So, could you go over the timing script? Sure. So, what we have here is the timing script. The timing script will run your code in all 3 modes: mode 0, mode 1, mode 2. Only do this after you've gotten all 3 versions tested and debugged. Then you're going to run a lot of code. And don't wait to the last minute to do this because the server starts crying. It is a 2-core system where you have something like 70 people in this class all hammering it at the same time. So 2 cores, 70 students. It's okay until people start running their runs on it for hours at a time. And the server will be weeping on Tuesday night. Okay. So what this timing code does, it runs your code in mode 0, which is, linear, I think, and then it runs it in mode 1, which is chaining, then it runs in mode 2, which is double or quadratic or standard library. And then it's going to search for every file in the local directory called insert search. And you're going to change this. You're going to change this to be whatever your file names are, because you're going to be making these files. Because I've given you a couple of them, but you're going to have to make 120 of them. Okay. And it's going to run your code on every file named insert search, and it runs it 5 times. and then it reports the time. So it's going to give you the running time of your code in linear mode, in double hashing mode, in chaining mode, 5 times for insert search 10K, insert search 20K, insert search 30K. Okay. Or run it on your own machine after you watch today's workshop. Yeah, so Mincorelli at 4:30 is going to give a workshop on every time Betancourt does that, I just delete the image. It just disturbs me seeing orange juice pouring out like that. So, yeah, if you want to learn how to set up your own Linux box and run it on that, highly recommended. Mincorelli is going to be showing you how to do that at 4:30. It's, in fact, great timing for that because server's going to suck Tuesday night. So if you run all your jobs locally on your own machine, you can write the report. It'll probably go a lot faster. Your machine's probably faster than the server, even when it's unloaded. Are you making your own test cases? Yes, you will. I'm giving you a couple so you can see what they look like. Insert search 100K, insert search 200K, etc., etc. You got to make your own. So how do you make your own? Well, I have given you a program that will generate input files, and you need to modify this and understand it. And welcome to grad school. This is exactly what grad school is like. So you have to make the inputs yourself. You have to run the timings yourself. You have to write the report yourself. The easy part of this assignment is actually doing the hash tables. You should be able to pass the 10 points for correctness pretty easily, because I've given you like 2 of the 3 solutions already. So that's the easy part. Then you got to like make the input files and then have the timing script run it and get all the data and like put it into Excel, graph it, write up a 1 or 2 page report. It's a 20 page. This is a 20-point assignment for a reason, because what I found was when it was 10 points, nobody would do it. Okay. So Sims is unsure about this. Let's look at the generator then. Okay. So what does this do? So this is the whole thing. It's 1 page of code. Okay. So it takes a command line parameter, and you run the program like this: generator 200,000, and that passes in 200,000 as argv1. These are the arguments, the command line parameters, and then it randomly seeds the random number generator, makes a vector filled with numbers, prints out a bunch of inserts to the screen, and then right now what's it doing? So if you typed in 200,000, it would make 200,000 inserts. It will then make 100,000 removes, randomly picking. Do you see what it's doing here? It's randomly picking elements out of the vector. So it's going to insert 100,000 times, and then, or 200,000 times, then generate 100,000 random deletes, and then it will do 100,000 random searches, some of which are still in there, some of which are not in there anymore. You can delete these 4 lines here, they don't do anything. And you probably need to... Yeah. And if you want your code to like do multiple... if you want to make multiple files at the same time, you can do something like this, where the first time through it's size 10,000, next time through it's size 20,000, whatever. And each one of these you write to a different file or something. So, figure it out. I got a negative review on Rate My Professor once when students like, what should I do? And I said, figure it out. He didn't tell me exactly what I need to do. Yeah, figure it out. So this code here will generate a, this is remove and search. So it'll do 200,000 inserts followed by 100,000 removes, 100,000 searches. So you'd use this for the combo timings. And so you just run this program 10 times, right? And this is how you redirect output. So this says write the results of the generator into this file. Let me show you how that works real fast. I know we've gone over this before, but it's worth going over it again. So if I say generator 10, so generator 10 is going to make 10 inserts, 5 removes, 5 searches, or whatever, 10 searches, whatever. And so if I write this into flu 10, then that file now has the thing in it. So the single right arrow, it takes the output of a program and writes it into a file. Very useful. The more Unix you know, the more powerful you will become. Okay. And then you can do generator 20 into flu 20. And then flu 20 has 20 inserts and 10 removes and 20 searches in it. Okay. So just make 120. Just make 120 input files. And if you want to automate that, go for it. Yeah, you need to make 120 input files. If anyone puts a negative review for Carnegie forever, you know, it's a web developer. That's funny. How do I do it, Professor? Get good. Yeah, I mean, it's sort of a thing, right? Like, you especially in CSI 40, you need to help people with like everything, right? Like if they don't know they need a semicolon, there's nothing, like, you can't be like, well, what do you think's missing? Like, it's not helpful, right? But for an assignment like this, it's like, all right, you need to make 120 input files. I've given you source code here that kind of, that's the executable again. I've got a source code here that will kind of do one for you. It's doing insert, remove, and search. You should be able to go from this to like just doing insert and search. There you go. This will do insert, search. Do 10 of those, right? Like, part of computer science is like taking what you're given and adapting it to different solutions, and that's kind of what I want you to do. Can you put the input files into a directory and run that? This assignment doesn't seem that bad. Good. Yeah, but this is like what you do in grad school. Like, it's a big part of grad school. And in grad school, you might like parallelize it. You know, like, all right, what can we do to speed up the hash table on a 10-core system? You know, things like that. It's a general idea. Yeah. I don't know why you're crying over grad school. Like, grad school's easy. Should all go. What about bachelor's? Well, this is bachelor's. So, grad school is very easy. Yeah, grad school is very easy. Bachelor's is harder than grad school, for sure. Yeah, and I'm not saying that like ironically or something. Like, in grad school, you mostly just like there's some core classes that are hard. You know, like you take data structures now with me. You take data structures again as a junior. You take data structures again as a grad student. And grad data structures are hard. Okay. You take algorithms as a junior. You take algorithms again in grad school, and it's hard. There's a couple grad classes that everybody takes that are hard. Most of grad school, though, is this. You sit in a table in a conference room. It's not in a classroom. It's just a conference room. There's a table, the professor's there. There's like 10 students. And he hands out papers. You read the paper. You talk about it. You get an A. That's grad school. Typically, you do a project, right? So like, hey, this paper talked about a way of doing a multi-threaded hash map. I'm going to try and implement that. All right, Bill, you're doing that one. All right, Blake, which one do you want to do? Oh, I like this idea over here. I'm going to implement it. All right, cool. And then towards the end of the semester, everybody starts presenting their things. All right, Bill, Blake, you're presenting on Tuesday. Aaron, Alexander, you're presenting on Friday. You know, whatever. And then, you know, just people go up and they're like, all right, this is what I did this semester. I implemented a multi-threaded hash table. Here's the performance. Here's some graphs. It shows you that it doesn't work very well on small sizes, but on bigger sizes, we get some nice gains. And you just turn in your paper and you have some graphs. You do a little PowerPoint. I can probably find some of them if you want to see it. I'm going to see some of my old stuff. It's from March of 2000. Yeah. So, Reducing problems, small size, medium size, large size. Quad tree based solution, that's a data structure, by the way, quad tree. And did some things, got some benefits. Got some timings on here at 440 megahertz, so that was fast back then, not fast now. 9 million locations in 4.8 seconds, 2.2 million, 1.2 seconds. You know, things, future, limitations, summary. Yeah, that was the semester. Yeah. Sometimes you write a report or whatever. It's like multi-threaded. This, and we do this, and on that, and yeah, that's basically grad school, you know. They had slide presentations in 2000. It's funny. Okay, so what makes junior level data structures harder? Are they more complex? Yeah, like in like, okay, for example, in junior level data structures, you'll do like a balanced binary search tree. In this class, we did an unbalanced tree. Very easy to write, very easy to code for. In junior level, you have to do like a red-black tree or an AVL tree, where the trees balance themselves. It's harder. It's just harder, you know. In junior level data structures, they'll make you do double hashing, for example. In this class, I make you do double hashing. So you've already kind of done that one. I actually cover a lot of junior level data structures. So let's see what else. Sets, merging sets, how to merge sets quickly. I don't know. It's more of the same. It's harder. You did quad trees in 50B. Yeah, I teach quad trees in IS 50B. Yeah. Okay. Can you give 45 an AVL tree assignment in assembly? Nah. C++. That's all right. I got plans for the assembly class. We're gonna be doing assembly games, I think. That's the plan. Yeah. So, yeah, the good news is in grad school, like most of it is just sitting around, talking, reading papers. You do your work, you get an A. Yeah, it's not bad. You're in a real gamer till you game in assembly. Exactly. You're not. So CSI 45 is assembly programming. And assembly programming, I'll show you what that looks like. CSI 45 is really fun. Right, so for CSI 45, oh, did I not push out Locksmith 3? Oh, I see. I guess I never did. Okay. So this is assembly. And basically, it's just each of the individual commands that a CPU runs. Adding, subtracting, loading, moving from one register to another, function calls, things like that. It takes a couple weeks to learn all the different assembly commands, and then it's all just in this long vertical column. For this assignment, they're given a disassembled program, and they have to remove the password protection on it. So the code is password protected, and they need to break the copy protection on it so that it will accept any password and play the game. And yeah, and so that's the thing, right? Like you're looking at this, and you're just like, all right, what the hell is going on, right? But I think probably most of the students in the class were able to break the copy protection on this in 15 minutes or less. It's only a couple pages, right? And so after you understand what's happening, branch compare two values, branch of equal to L3, load, print. So L3 loads from L4 plus 16. This one loads from L4 plus 16 plus 24. You know, somewhere within here, it's checking to see if the password is 42. And all they need to do is change this thing here from a branch if it's equal to password accepted to branch always, and that's the entire homework assignment. So, if that doesn't excite you, so you have to write functions in assembly and things like that, and a lot of times you can beat the compiler. You can write code that's faster than the compiler by writing it in assembly. So that's kind of it's like a completely different language. Your stomach hurts looking at this. Somebody's going to kill you and excite you at the same time. You don't have to take 45. You should take 45. It's a very fun class. Yeah, Ben Cord is like terrified of the Pi assignments for some reason, but that's actually a lot of fun. So what you do is you get a Raspberry Pi, and in your code on the Raspberry Pi, you can turn these different pins on and off and use them to control lights and motors and fans and sensors and things like that. So you can actually interface your code with the real world. It's a lot of fun. Yeah, you definitely. I like what your hairline word is. No 45 for you. Now 45 is it's a class I don't want to say you have to take it, but you should have to take it. Where are you going to go to where are you transferring to, Sims? Santa Cruz. Yeah, I mean every college has some sort of like systems programming, you know, and if you don't take it, then yeah, computer systems. Right there. So, maybe you can get by without taking it, but I wouldn't. Like, it's actually a really important class to take. So, yeah, especially if you're going to be in game design. Like, game design people need every ounce of performance they can get, you know? And in assembly, you learn all about, like, speed in a variety of ways. So, yeah, I wouldn't say it's hard at all either. So here's FizzBuzz in assembly. So we add 1 to X, print it. 1 to X, print it. Print fizz. Add 2, print it, print fuzz. Like, add 3, print. Add 1, print. Subtract 1, branch to the bottom. I don't know. There's only a few commands. Like, the really nice thing about assembly is that there's add, there's subtract, there's function call, move one thing from another. That's it. And if you can do that, you can, like, it. Yeah, it looks scary, but it's not. It's fun. Okay. You're gonna learn ASM, like it or not. Yeah. Yeah, and basically, if you're going to be doing games programming, you know, games are all about speed, so you need to know that kind of stuff. All right, assembly's still harder than C++. I mean, you don't want to write a whole program in assembly, right? Like, you're not going to write Microsoft Word in assembly. But, like, let me show you what people actually do, right? It's like, non-ironically, right? Right. So this person was posting a bug in the CPP questions channel saying the release mode was slower than debug mode. And so the person said, non-ironically, it's probably a bug, and debugging standard library release code isn't fun. I would compare the disassembly to see if you see anything funny. You can only do that, Sims, if you know how to read assembly. You know? And so what people do all the time is they use a website called Godbolt, and they'll .org. League's pathfinding code is in assembly. Yeah, their particle code's in assembly. Yeah, so you don't write whole projects in it because C++ is easier to organize. But you kind of have to know assembly for like things like this. So let me show you. Okay, so So this code, it's funny, it's just doing the addition automatically. And so what you do is you look at your C++ code, and then you look at the assembly that comes out of it, and you see if it's like stupid or not. Like this is something that people do all the time. Where like you're like, all right, I have this idea, I'm going to try using an optional, and then use an optional, and all of a sudden your code is like 500 times slower. You're like, all right, what the hell's going on? And so what you do is you put your code up, your C++ code up here, you look at your assembly code over there, and you try to see if what's coming out is like stupid or not, right? This is something we actually do like all the time, where like if you want to see if your code's any good, you know, or if the optimizer is working or whatever, you open up Compiler Explorer, you punch in some C++ code, and you see what assembly you get. And in order to do that, you have to know assembly, right? You have to be able to look at the assembly and be like, yeah, that looks reasonable to me, or that looks stupid. Why are you doing that? You know. And so even if you don't write assembly, like just you can mouse over the different lines and it shows you which lines correspond to which lines of C++ code, things like that. So yeah, it's a very important skill to have. By the time you have more experience, it'll seem less daunting. Yeah, just take it. It's yeah. The amount of code you write in assembly is actually not that big. More about reading assembly than writing assembly a lot of times. Yeah, like in real life. A lot of times you don't write assembly. You just look at it and just make sure that what you're getting looks reasonable. If it's doing something like really crazy, you're like, you know, let me see if I can figure out what's going on over in the C++ side of things so that the compiler doesn't generate bad assembly code, things like that. Okay, so should you take 26 or 45? You should take both. 26 will be offered in the fall by me. Lawton is teaching 45 in the fall. And the schedule, if you haven't checked the schedule, it should be updated. The one thing that I have yet to hear word on yet is if 26 will be hybrid or not. We talked about it. So far it's currently listed only as being in person on the schedule, but we'll see if that's a thing. Physics 4B, 4C, that'll kill you more, probably. Yeah. Lawton teaches x86. Yeah, that's fine. You'll only be at CCC for the summer and fall. Yeah. Then take 45 in the fall. Fun. Take 26 with me. You can take both at the same time. They don't rely on each other. Well, the times changed for 26. 26 is going to be at 9 o'clock in the morning. I'm sorry. But it was the only way that we could get it around the physics labs. The physics labs are start at like 12, I think. for 4B and 12:30 for 4C on Tuesdays and Thursdays. And so there's no way of doing it except by just moving 26 up earlier. So yeah, 9 a.m. is going to be the start time for it. Yep, no problem, Ash. Yeah, discrete math is important. Assembly is important. All right, I'm just going to log off now. I think this is a pretty good day. Online in person. The plan is for it to be online and in person. We'll see. We'll see how it goes. And up next is Min Corelli with a workshop on how to install Linux on your Windows machine. Right. See you, everyone. Have a good weekend.